Welcome to GR of Mathematics and Statistics lessons. Today we are going to be considering circle geometry part 2, where we'll be talking about circle theorems. But to aid our understanding of this particular section on circle geometry, we are going to be considering some definitions that lead to what we want to do. Okay, so let's start with a definition of geometry itself. So what is geometry? Geometry is simply a branch of mathematics that studies the properties and relations of points, lines, surfaces, solids, and higher dimensional analogues. Okay, so some textbooks will tell you that geometry is the study of the properties of shapes, whether plane or solid. In a sense, it is also correct. So geometry is a branch of mathematics that studies the properties and relations of points, lines, surfaces, solids, and higher dimensional analogues. So let us consider two categories of geometry. Now take note, geometry is an ancient concept in mathematics that dates back to more than 2,000 years when it was discovered or pioneered by Euclid, the Greek mathematician. So, but in recent times, other ideologies or concepts on geometry have emerged. So that brings about two categories of geometry. So if you're studying geometry, it means you may just be studying Euclidean geometry, what is called Euclidean geometry, or you'll be studying what is called non-Euclidean geometry. So there are two categories of geometry: Euclidean geometry or non-Euclidean geometry. Okay, now one thing you must take note of is that whether Euclidean or non-Euclidean, you just may be studying plain Euclidean geometry, solid Euclidean geometry, or higher dimensional Euclidean geometry, or you may be studying plain non-Euclidean geometry, solid non-Euclidean geometry, or higher dimensional non-Euclidean geometry. So please take note, whether plain or whether Euclidean or non-Euclidean, you may be studying plain, solid, or higher dimensional geometry. Okay, now as the circle is a plane shape, it is only proper for us to be discussing along that direction. So I'm going to be considering Euclidean plane geometry. Why am I considering Euclidean plane geometry? It's simply because circles are plane shapes. Okay, and in plane geometry, what we study are the properties of two-dimensional shapes or plane shape, the properties of plane shapes. So since the circle is a plane shape, it's only proper for us to be looking at it from the aspect of what? Plane geometry. And because our focus is on the Euclidean geometry, we will be calling this section Euclidean plane geometry. So Euclidean plane geometry focuses on the properties of plane shapes or two-dimensional shapes. Okay, now that brings us to the definition of what circle geometry is. So in circle geometry, we'll be considering, and we are more or less considering an aspect of Euclidean plane geometry that is concerned with the theorems and properties on circles. So when we say we are studying plane geometry or circle theorems, as it may be called in other textbooks or online sources, take note, what we are referring to is that aspect of Euclidean plane geometry that is concerned with theorems and properties on circles. Now, in our discussion here, we will be considering 8 of the theorems in circle geometry. That is not to say that there are only 8 theorems. Take note, there are more than 8 theorems in circle geometry, but in our discussion we will be considering 8. Now these 8 theorems we are going to be looking at in our lesson on circle geometry part 2, I'm going to be categorizing them into 4 groups for better understanding. Okay, so what 4 groups am I going to be considering my theorems? The first group will be the theorems on chords. The second group will be the theorems on arcs and segments. The third group will be the theorems on cyclic quadrilaterals, while the fourth group will be the theorems or properties on alternate segments. So first group of theorems on chords. Second group of theorems on arcs and segments. Third group of theorems on cyclic quadrilaterals. And then fourth and final group of theorems in our discussion will be the properties and properties on tangents, and then theorems on alternate segments. So quickly, let us go into the first category, theorems on chords. Now, under theorems on chords, we'll be considering 2 theorems, Theorem 1 and Theorem 2. That is not to say on the internet or any other sources you consider you will be finding this theorem consistently as theorem 1 and theorem 2. No, I'm only the one using theorem 1 to describe this theorem and theorem 2 to describe the theorem. Okay, so it mustn't be found on the internet as theorem 1 and theorem 2. No. So please understand the theorem, not the theorem number. That's what I'm trying to say. So let's start with the first theorem on chord. The first theorem states that a perpendicular line drawn from the center of a circle to a chord which is not a diameter will do something to that chord. What will it do to the chord? It will bisect the chord. So when a perpendicular line is drawn from the center of a circle to meet a chord that is not a diameter, that perpendicular line will divide the chord into two equal parts. In other words, it will bisect the chord. Now, the second theorem, theorem 2, is a corollary to theorem 1, meaning that theorem 2 is a consequence of theorem 1, or another way of stating theorem 1. So what does theorem 2 say? It says that a straight line, in theorem 1 we were referring to a particular type of line, a perpendicular line, but in theorem 2 we are referring to a straight line, and when a straight line is drawn from the center of a circle to a chord which is also not a diameter and which in addition bisects that chord, it will be perpendicular to the chord. So a straight line drawn from the center of a circle to a chord which is not a diameter and which bisects the chord is perpendicular to the chord. That is what theorem 2 states. And take note, theorem 2 is a consequence of theorem 1. That's why it is called a corollary to theorem 1. Now, please take note, a theorem is a complex mathematical statement, and whenever a theorem is stated, it must have a proof. So you don't state theorems without proving them. We are going to be proving every theorem I mentioned in this lesson in our part 3 of circle geometry. So watch out for our part 3 video on circle geometry, where we'll be considering the proof to all these theorems mentioned in our discussion. So let's go to the second category of theorems. We call the second category of theorems in our discussion theorems on arcs and segments. So under theorems on arcs and segments, I'm going to be considering three theorems, theorems 3, 4, and 5. What does theorem 3 state? Theorem 3 states that the angle which an arc of a circle subtends at the center of a circle is twice the angle which is subtends at the remaining part of the circumference. I would like you to use the word cover to replace that word subtends if you don't understand the word subtend. So it more or less tells you that the angle which an arc of a circle covers at the center of the circle is equal to 2 times the angle which it covers at the remaining part of the circumference. So we are going to be proving this theorem in our part 3 video on circle geometry. Theorem 4 is a straightforward theorem. It says angles in the same segment are equal. Angles in the same segment are equal. So we are going to be proving this theorem also. Let's go to theorem 5. Theorem 5 states that the angle in a semicircle is a right angle. So any angle in a semicircle is a right angle, and we are also going to be proving this theorem. So that being said, those are the 3 theorems we are going to be considering under the second category of theorems, being theorems on arcs and segments. So let's go to the third category of theorems. These are theorems on cyclic quadrilateral. If you remember, or if you have watched our video on circle geometry part 1, you must have seen that we discussed the cyclic quadrilateral in that video. So please, to understand cyclic quadrilaterals, quickly watch our videos on circle geometry part 1. Watch our video on circle geometry part 1. You would understand the concept of cyclic quadrilateral better. So we are going to be taking 2 theorems on cyclic quadrilaterals, theorem 6 and theorem 7. So theorem 6 states that the exterior angle formed on one side of a cyclic quadrilateral is equal to its opposite interior angle. So this exterior angle formed on one side of a cyclic quadrilateral is equal to the opposite interior angle. That's theorem 6. Theorem 7 states that opposite angles of a cyclic quadrilateral are supplementary. Supplementary in the sense that the 2 angles opposite one another in a cyclic quadrilateral add up to give 180 degrees. 2 angles and only 2 angles are supplementary when they add up to 180 degrees. But 2 angles are complementary when they add up to 90 degrees. Take note of that. So when the theorem states that opposite angles of a cyclic quadrilateral are supplementary, it means that opposite angles of a cyclic quadrilateral add up to 180 degrees. Okay, so let's go to properties on tangents. You know, the third group of theorems and properties pertain to tangents and alternate segments. So let's look at properties on tangents. We are going to be looking at two properties. I'm going to be summarizing my properties on tangent into two. So the first property on tangent states that a straight line drawn from the center of a circle and through the point of contact of a tangent to the circle is perpendicular to the tangent and vice versa. I'm going to be explaining this particular property using a diagram that follows next. Okay, so the property 2 states that when two tangents are drawn from the same exterior point or a common exterior point to two different sides of the circle, then two things emerge. Number one, the straight line joining the exterior point to the center of the circle bisects the angle at the center as well as the angle at the exterior point. I'm going to be explaining this. Then number two consequence of this property is that the straight line joining the exterior point to the center of the circle partitions, please. It partitions that straight line partitions. So I'm going to cancel this. The straight line partitions the quadrilateral formed into two right angle triangles. So when two tangents are drawn from the same exterior point to two different sides of a circle, then something happens. The first thing that happens is that the straight line joining the exterior point to the center of the circle bisects the angle at the center as well as the angle at the exterior point. It also does another thing. The second thing it does is that the straight line joining the exterior point to the center of the circle partitions the quadrilateral formed into two right angle triangles. So the quadrilateral form is partitioned also by that straight line. So we are going to be seeing this in the diagram that follows. Now, notice for the property 1 on tangents that when a straight line is drawn from the center of a circle through the point of contact of a tangent to that circle, this straight line forms an angle 90 degrees and vice versa, meaning that if you draw the straight line not from the center of the circle but from the point of contact of that tangent to the circle to the center of the circle, the angle formed is still what? It's still 90 degrees. Then the second property we just stated was that when when from a common exterior point or from an exterior point, two tangents, this tangent and that tangent, are drawn to a circle from the common exterior point, then something happens. This straight line that is drawn will be a bisector, such that what it means is that this straight line OB that is drawn from this common exterior point would now form an angle here that is also equal to this angle. So in that sense, the straight line becomes a bisector, an angular bisector, to the angle formed at the common exterior point. It is also a bisector to this angle formed at center. That's what we are saying. So the first thing that this straight line does, the straight line drawn from the center to the center of the circle, that is from the common exterior point to the center of the circle, the straight line first of all does one thing. It becomes a bisector to this angle here and this angle here. Now, secondly, the straight line partitions this shape. This shape BAOC is a shape the straight line will partition into two. Sorry, I called this a quadrilateral, the shape a quadrilateral. What I meant is that the shape in question is partitioned into two equal parts. You would see that this straight line partitions this shape into ABO or BAO, sorry, and BCO. So, of course, the shape in question is a quadrilateral because it is a four-sided plane shape, BAOC. Okay, so when this straight line is drawn, it partitions this quadrilateral BAOC into two right angle triangles. Right angle triangle BAO and right angle triangle BCO. Okay, now why are these angles here 90 degrees? They are 90 degrees because of theorem or property 1 on tangents. Now, going to theorem 8. Theorem 8 is the theorem on alternate segments. Okay, this particular theorem has two proofs. We are going to be using two proofs to prove this particular theorem when we get to our third video on circle geometry. Okay, so the theorem states that the angle formed between a chord and a tangent through the point of contact of the tangent to the circle is equal to the angle formed in the alternate segment. So the theorem is straightforward. It says the angle formed between a chord and a tangent through the point of contact of the tangent to the circle is equal to the angle formed on the alternate segment. Okay, so that being said, please like our video, share our video, make comments on our video, and most importantly, subscribe to our YouTube channel, and I'll be seeing you on our next class, on circle geometry, being circle geometry part 3, where we are going to be proving all these theorems. Thank you very much.